let me start with the screen share here. Just repeating what I just said. I have a CS major that's coming in at 4:30. You can join my Zoom room then if you want to find out about that. Whoa, I don't want that yet. Um, and then I'm going to try and do slightly different problems in this lecture than I did in the previous lecture. So if you're watching both of the old live streams, that can hopefully help you get some of your homework done if you want to work along with me that way. That said, let's get back and start with a brief introduction here. This introduction is exactly the same as the other time. I just want to point out a few things that we talked about last time and how we're going to try and use that. We talked about these definitions. At the end of today's lecture, boy, it sure would be a good time to read a book. If you read a book after we do today's lecture, a lot of this stuff will start to make more sense and what I mean by these things and things like that. So make sure you read a book regarding all these definitions and lock in some of the concepts. There's three pieces to doing, well, I guess four. There's being able to understand a concept, being able to calculate something, being able to code it up, and also to clearly communicate. So, right, you got to be able to do all those things as a scientist. So this would be a good time to read a book so that you get better at understanding the concepts of these things. That said, we rapidly mentioned that, hey, look out, and we're going to do a bunch of equations that look like this stuff down here, and all the I-hats drop out. So we're going to remember that even though these strictly are vectors up here, or say, let's say for X, right? X is a vector. When we come down into here, we're going to hide that. And so we aren't going to see the vector, but you're supposed to know it's a vector. Next, we said, scrolling down, we mentioned a few of these things. In particular, we mentioned how tricky things are when they're going backwards. And we mentioned this stuff. If something has a negative velocity and a negative acceleration, negative velocity, v less than 0, negative acceleration, there's a case where you can actually be speeding up, right? You get more and more negative velocity. That's a larger and larger speed. So just be aware of that. And then we also mentioned that we have to be careful whenever objects reverse direction, the problems we need to pay attention to, velocity versus speed, or displacement versus distance in particular. Most students like to think that distance is the absolute value of displacement. That's true as long as you're always moving in one direction. But if you ever reverse direction, not true anymore. Okay. The next thing we said last time was this. We said, hey, these equations that we're using down here, we're going to use these over and over and over again. We made these special comments about the different ways people might write V initial versus V0x. We said that delta x is the same thing as final minus initial. And we said that you could write it this way or this way. And the fact remains, something students forget is, remember, this is only valid for constant acceleration. So that's a big deal. This is only valid for constant acceleration. So later on in your physics classes, we won't always be able to use these equations. Now, it turns out if we learn how to code in a computer program, we could split up problems which do not have constant acceleration into smaller pieces. And on each one of those smaller pieces, it's approximately constant acceleration. And then we can do this trick. That trick is basically calculus. All right, so we said, I think, all of those things last time. Furthermore, we said this. We're going to have this strategy. We're going to try and read a problem, draw a picture, label it, identify some stuff, and write some equations. And I just want to point out, there's one thing in here more than all the others: reading. Students are bad at physics when they start because they haven't had to be held accountable for their ability to read. You are now going to be held accountable for your inability to read. Okay, so if you don't read the question and you don't answer exactly what was asked, you keep losing points. And actually, Canvas quizzes, whether you like them or not, is actually good for reinforcing that habit. And I realize it's a little worse than it should be, so I understand that. But the fact remains is, boy, you are expected to read questions carefully. And if it says speed, that means one thing. If it says velocity, that means a different thing. They are related, but they're not exactly the same, just like distance and displacement, et cetera, et cetera. So we always have to look out. And one of the big things that this matters is, will you get a minus sign? For example, if something's moving to the left with a certain speed, Speed is always positive, but that velocity would be negative. All right. And so, yeah, all right, let's leave it at that. Notice this, the very last two steps. I guess let's do the last three. First, do the problems without plugging in the numbers. Why? Because it will save you time and frustration over the long run. Are you going to like this on day one? Absolutely not. But by the time you become even next semester, you are going to hate putting in numbers. It takes longer and it increases your odds of making mistakes. So what we want to do is learn how to solve problems algebraically, then plug in the numbers at the very last possible moment. Finally, this is a step that maybe you don't always get in a math class. Check. We always want to check the units. Does our answer kind of make sense? What about the plus or minus sign? Always check your plus minus signs on everything you write and everything you end up solving for. Are we supposed to include a plus minus or not? And lastly, the approximate size. So you could say the order of magnitude and reasonability. This is basically just saying, is the numbers seem about right given the situation? All right, so that's what we're going to work on. Last time, oh, and let me get to the chat. Okay, all right. And then keep going. Last time we did question 2.14 and kind of started that. We maybe didn't finish the whole thing, but I'm going to remember the live stream, we did most of that, and you could probably finish the rest using the workbook. In the earlier section today, I covered 2.1 and a half. So I thought it would be logical to go to 2.1 and 3/4. So we're going to start here today, 2.1 and 3/4. And I see a note to myself. Okay. So what I'm going to do right now is I'm going to get this picture drawn up on my whiteboard, and then I'll adjust the level of the computer screen and et cetera, et cetera. So right now, why don't you get this written down on your paper, and we can all see how we compare after we do our pictures and drawing. So draw, label, all that stuff. Okay, let's see what we do here. All right. Hold on a sec. Like I said, I'll line up the whiteboard later. So get out a piece of paper and practice writing this stuff down. Okay. I like to let the paper do the work for me. So I try to get everything I can on the paper, and we'll discuss this. Maybe don't look at my little window right now and just try and write down what you think should be written down, and I'll write down what I think should be written down, and we'll compare. Let's start there. Okay, so I'm going to go ahead and get this off the screen, and I've probably got most of the numbers off the page. So, oops. All right, so this is how I started drawing it. Is there more I could do? Of course, but this gives us a start. Just give me a second here. Some things that I drew. Number one, I wrote down the problem number so I could find this later if I'm working on it. Two, the problem said it was a 100-meter dash, so I make sure and label the entire race 100 meters. Now, I made the assumption that it's 100.0 meters. You might be wondering about the sig figs. I figure, yeah, they probably don't screw up by 10 centimeters when they're doing an official race. So that's about the thickness of the line. So I think it's totally reasonable to have that sig fig there. If you don't yeah, who cares? Whatever, I'm putting that sig fig on there. They said the first portion of the race was 15 meters. And then I said, well, 100 minus 15, that should be 85 to get the last half or the last portion of the race. Finally, they said they accelerated this rate for the first portion of the race. Now, there's probably some more information there. We probably know, let's see. She's accelerated from rest. Well, that means the initial speed or the initial velocity is equal to 0. Okay. And then lastly, there was a comment made where this person finishes the race at the top speed. Now I'm going to try and see if I can get somebody to pipe in here on the Zoom, even though it's not fun at all. When they finish the race at the same speed, what do you think the acceleration is? The last
0.
portion. Yeah. So notice the problem statement doesn't say it exactly this way, but they implied constant speed to finish race. That tells us that A sub x equals 0 for stage 2. Now, you're going to notice we have a lot of subscripts in this problem. For example, it says the initial velocity is 0. So I'm going to say the velocity for stage 1 initially in the x direction equals 0. What? Again, for the first stage of this problem, the blue phase, the first stage has an initial velocity in the x direction of 0 because the problem said started from rest. So you're supposed to understand everything about how this explains all of this sentence. This is basically a full sentence, right? The initial speed at the start of the race is 0 in the x direction. That's a long sentence, and we've made it a lot shorter by using these subscripts in a clever way. All right, so at this point, I think we're doing all right. Any questions about this phase? I'll just go to gallery view. And feel free, again, chime in at any time. I think Memo had to just texted me. He said he had to step out for a second. He'll be right back. So Memo's not here right now. But yeah, if you need to ask any questions, this is a good time. And don't be shy. A lot of times, whenever one student asks, everybody else is thinking it. Oh, Memo is back. Remember, my bad. Sorry about that. Okay, so you could also chat with Memo if you need to instead. All right. All right, let's keep going now. So let me get this back up. I'm trying to follow our strategy, so let's just kind of see where we're at here. Again, I have read the problem. I drew some pictures. It's getting pretty well labeled. Looks like I'm up to this step. Identify a list of knowns and unknowns. Now, with this particular problem, it's very confusing. We have 2 different sets of unknowns. So I'm going to keep track of them with colors. You could also keep track of them with putting a dotted line down the page like this. And so you could say everything for stage, whoops, that's kind of crooked. Everything for stage 1 is on this side. Everything for stage 2 is on that side, whatever. But the idea is, remember from last time, we said there's 5 variables that appear in our equations. Delta x, the initial x, the final x, a sub x, and time. And I'm going to do that over here as well. And like I said earlier, this is all stage 1. So I might even stick a 1 down in here. And again, the order doesn't matter. They might not have the same time. Whoops, that's a little bit. Let me see if I can go down just a. There we go. So they might not have the same time, right? It probably takes a different amount of time to run this portion and that portion of the race. So we need to have different times, different accelerations, different speeds perhaps, and different values of x, or delta x in this case. So, all right, in this case, you could kind of think to yourself what you should punch in all these, but I'm going to go ahead and do it myself. I know for the first stage, this is positive 15.0 meters. You don't need to write the plus sign. I'm just trying to do that for emphasis. Do you agree it goes to the right? I think most people have no trouble thinking of this as the positive x direction and this as the positive y direction. Oh, I got something up there. Whatever that is, who cares? Sorry about that. So in this case, whatever we usually think of going to the right as positive and going upward. So 15 meters to the right is a positive 15 meters. This one said it started from rest. That tells me this is 0 meters per second. I'll put the units on just for practice. Obviously 0, you don't need to write any units on because 0 is going to be 0. The final velocity, I don't know what that is. The acceleration was given to us. And then the time, I didn't see that anywhere. This is what a lot of these things look like in a physics class. Usually you have, in these one-dimensional kinematics problems, you'll have 5 things, and you'll know 3 of them. And usually at least one of them you have to get from the words of the problem. Very typical, right? So we say, aha, there's a distance, there's an acceleration. Oh, it said from rest. That's how I get my third known quantity. Okay, next let's go over to this side. For this side, I know this is, and it's positive. I don't know this speed, but I do know this acceleration down here, right? We mentioned that it's constant speed. So again, one of these words in the problem told us this. I don't know the time. Oh man, I don't know the final speed. I don't know the initial speed. Oh boy, are we in trouble? Didn't I just say you usually know 3 of the things and you could figure the other 2 out? With this one, we only know 2 of the things. How are we ever going to do it? What's the trick? Does anybody see a connection between the red parts and the blue parts? Go ahead.
The final for the first part is going to be the initial for the second part.
Absolutely. And then how does the initial for the second part compare to the final for the second part?
Aren't they the same thing?
Exactly, because it's not changing. Nice. So notice that this number, if we can get it, is going to help us with both of those pieces. So this is, I would call this a 2-stage problem, where basically we're doing a kinematics problem, and then we use part of that for the next kinematics problem. This is very typical. Okay. So that was great. I don't know who that was, but thank you for chiming in. I appreciate it. Oh, that's another thing. If you're worried about, sounding stupid, by the way, I have no idea who's talking most of the time. So obviously you notice I recognize people eventually after about 10 questions, but yeah, so, all right. Yeah, you don't have to worry about sounding stupid in this class. Everybody is having trouble with this too, okay? All right, that's the list of knowns and unknowns. To be honest, this is most of the physics. The rest of it is usually just math. A lot of the physics comes from understanding the words, the communication, whether you put in zeros. A lot of it relates to plus minus signs. A lot of the physics is trying to understand when, in which situations would we put in a negative or a positive, etc. Okay, so after this, it's all just math. Let's see where we are at in our problem solving strategy. All right. Where are we? We read, we drew, we labeled, we did a bunch of crap. Next up would be equations. Now, I've run out of room here, so I'm going to do that in just a second. But I do want to point out the next stage is rereading. So that's the phase I want to emphasize. The reason you reread is think how long we've been going on this. There's a lot of stuff written down. Right before you start to do any real work is a good time to reread and make sure you have identified what you're trying to do. So I'm going to reread the question now and see what we're trying to do, and I'll bring it up on the screen. We've got a bunch of stuff there. So what are we trying to figure out? Aha, top speed, time for the race. So let's keep our eye on the prize. So what are we trying to figure out? Well, part A is top speed. I think you'll agree the top speed is the velocity right here, right? And so this is WTF. And though it's cheesy, what to find and keeping track of it is probably worth remembering at your stage, okay? Your early stage of your physics development. We want to keep an eye on the prize. What are we trying to find? This. So at that point, because I've run out of room, let's go jump to the solutions and see what it looks like a little bit. Unless there's questions, I'll pause for a second.
Time is also a WTF, right?
That's right. And so in the second part, we're going to have to get these. Yep. I was just focused on the first part. Good question. By the way, I'm not a huge Houston Rockets fan. This is just a free coffee cup with Jeremy Lin on it. I don't know. That's what I got here. Not a big Houston Rockets fan.
What are you drinking? Coffee?
Oh, green tea today. Green tea.
Okay.
So the lecture will only be moderately insane. All right. Okay, let's take a look at the solution and just catch up because again, just out of the physical constraints of the board here, 2.1.3. And by the way, I hope you notice in here, I've tried to be very detailed in the solution. So if you're having trouble and I'm not around, hopefully these actually make sense to you. So let's scroll down a little bit. And there, oh, you can see I've tried to, let me do this here. You'll notice that sometimes I'll even put little comments in here like this, like why I did this. And so I'm a big fan of trying to understand why. And yeah, like for example here, you might be able to do all the work in your head, but it is much easier to do this on paper. Okay, please follow the paper. So here's our equations, right? Here's our equations. Oh, this is something I definitely want to emphasize right here before I forget. The best thing to do when you get your equations immediately, because we know this thing is 0, before you do any algebra, plug in anything that is 0. Why? This gets out of here. This goes away. And this goes away. When you do that, the equations are so much simpler. So again, this cannot be underestimated. Anything that is equal to 0, get rid of it before you do the algebra stage, okay? So let me clear all those drawings and scoot down. When you do that, I hope you agree, these equations down here look a lot less intimidating than these equations up here. And this is pretty typical. Now, in this case, I'm going to look at them. This is another technique I do. Let me, just a second. Let me make this a little bit bigger. All right. And scroll down. So we know all these numbers, right? We know our list of knowns and unknowns. And if you check the things that you know and don't know, I look at it, I know this. And I know this, so I should be able to figure out the time. That's cool, but that's not what I'm trying to do in part A. I'll move on. I don't know this. I do know this, but I don't know that. That's just not a great equation for me to start with. Here, I'm looking for this. That's WTF. I know this. And I know this. This seems to me the logical equation to start with. And then obviously for the next part, I could use this equation up here. All right, so that's what goes through my brain when I'm reading this. And I want to pause and see if that made some sense. Again, you look at the equations, and before you just blindly plug in, take the time to think, is this one going to get me what I need? And if you're wondering where you get these equations from, you know the equations. You can find them on the back of your book, right there, that whole line across, or page whatever in your workbook. And if you write them out every time, within a week, you're going to have them memorized. So, all right. Just checking for questions. And remember, you can ask Memo. If you're like intimidated by me, just ask Memo in the chat private, okay? So I'm going to go ahead and keep cruising along here. And you can see, here's some things that I did. In this case, before I plug in any numbers, first I take the square root. Now, there's a tip here. In general, we always consider both the positive and minus square roots. But since this time the runner is running to the right, and this is a velocity, we expect this should be a positive number, so it's okay to keep the positive number. I can check the units of this equation really quick. The square root of 2a delta x, I'm going to check the units before I plug in any numbers. This is the square root of meters. Oops. Let me change the color. It's going to be meters per second squared times meters. The 2 has no units, and then I got to square root it. If I use meters and meters per second squared for these things, this actually has the correct units because it's the square root of meters squared over second squared, which is meters per second. And when you punch in the numbers, the idea of doing this is if you check the units separately, one, that gives you a check to see if you flip something upside down. If you get the wrong units, clearly you did something wrong. And two, the other thing is now I can punch the numbers in my calculator and I just take this and shove it on here and write the units. It's like we're doing the unit math separately from the number math. All right. And there I figured out the time for that stage, just like Esteban said. Couldn't we also get the time? You're right. Okay, and then notice some other things here. I checked the units. I converted this into miles per hour. That's pretty fast, but we do know this woman is a track star, so that's cool. And this time seems normal, right? 2 seconds, 2.5 seconds to accelerate, and then maybe 9 seconds to run the race or something, 10 seconds for a 100-yard dash. All right, let me pause and see here. All right, so hopefully you're following along at home. I know it's a little distracting when I'm scrolling and annotating, so hopefully that's making some sense. I see a question there. Yes, definitely Memo. So look at the chat there. That's good stuff. So definitely talk to Memo about the tutoring. Free tutoring, right? You could use it. I saw the quiz scores. Most of you can use the help, right? It's free. Use it. All right. All right. In the second stage, let's go ahead and finish this one out and see what happens in the second stage, since I don't see any questions popping up. And if you don't want to listen to me, you can just keep going. So in the final stage, you could just grab this one right here. And we know, now what I did there, I don't know if you can recognize this equation. Let me write it out. X2 final. Sorry, I have to do this on the screen instead of the whiteboard. I'm just trying to save that. Actually, I'm not going to do it this way. I'm going to do it this way. Sorry, I'm a little slow here. I know there's probably lag as well. The order of the subscripts doesn't matter to me. All right, so that's our kinematics equation from the back of the book. I know that this one is 0 for stage 2. And so this is basically the equation that you've got right here. I just solved it, right? So you could see that, what is, oh, and I should be careful. This is not t, it's t2, right? And so you can get that t2 is equal to delta x2, which I think we said was 85 or something, over v2 initial x, which, remember, we said this was equal to the final velocity from stage 1. v1 final x, oh, let me, the idea here is the final velocity in the x direction from stage 1 is equal to the initial velocity for stage 2. All right. And I think at this point, we know all the numbers. You could check the units. I'm going to do that really quick. Checking the units. That's going to be meters divided by meters per second. Now it's easy to screw this up. So what am I going to do? I'm going to multiply by the reciprocal on the top and the bottom so I don't screw it up. Whatever I do to the bottom, I'd better do to the top. And then I look at it and see, aha, I see that the meters drop out, the seconds drop out, this meters drops out, and I get seconds. That's the correct units for an answer of time. This looks like it should work out. And that unit check, again, is not always going to be correct, but it's definitely one way to tell that you're on the right path. Okay. All right. Let's stop the screen share there. I'll wait just a second, just in case. Any questions, go ahead and unmute. I can't see everybody right now. All right. Okay, just checking in. If possible, I know it's annoying on Zoom. Could you maybe try to give me some feedback? Is any of this making sense, or how are people feeling? Moderate, okay, a couple okays.
Slightly worse than moderate, I guess.
Okay, so is this getting a little bit better than maybe the first problem, and we just need to do more practice, kind of thing?
Yeah, definitely.
Yeah, exactly. All right. So, and that's what we're going to do next. We're going to do more and more of these problems. And I do hope that one of the things you see out of this, I appreciate the good feedback. Thanks, everybody. One of the things that you'll see here is, look, I didn't even have any room to do any work yet, right? These problems will get out of control if you don't find a way to be neat and organized. So this is a big piece of being a successful physics student. Starting early so you can have plenty of time to write out your work neatly and be organized and do enough practice so that you can feel like you can do this stuff in your sleep. On quiz days, you don't have time to go read through the workbook and find a comparable problem and relate it at that time. That's just not going to work. Yeah, and writing these patterns, I'm telling you, as the problems get harder and harder, like this one, I bet a number of you, if you just thought about it and sat there with a calculator in your hand and did trial and error for a little bit, I bet you could get this problem in like 30 minutes without writing anything down. What you'll see is writing this all down, you'll be faster on average, especially when new stuff starts coming at you, like a quiz question. So just make sure I address Jacob's stuff. Yeah, exactly. And that works, Jacob, but it's slow on average. Every once in a while, it's faster. But if you're faster 1 out of 10 times, and then maybe the same speed for 2 out of 10 times, but slower on 7 out of 10, it's not faster to do it in your head overall. It's faster to work things out on paper on average. Not always, but usually. All right. Yeah. I like to tell my students, let the paper do the work, right? If you get used to this, you're just putting it on paper and the problems will start doing themselves for you if you have a system and do them all the same way. That said, what is that system? That. Is there a faster way to do this stuff? No, this is the fastest way on average. All right. Next, let's try another one. And this next problem that I want to do is going to be a little bit weird for most students. We're going to do a problem without any variable or without any numbers in it. Okay. And yeah, so a lot of physics questions are going to start to look like this next one. So let me see. Let's look at 2.3 on page 24. Okay, I'm going to get to it. Screen share in just a sec. So this one right here, I don't know if I can get that a little bigger or not. Ooh. So that's this problem. I'm going to make it just a little bit. Let's make it 250. No. All right, there we go. So you can kind of see this problem now. We're looking at 2.3 here, and this is the one we're going to work on. And again, if you think you're good at this and don't really need this, some of you've had high school physics. That could be the case. See if you could do it without listening to me and try it yourself, then check the solutions. So we're going to try and do this problem. Earlier in the day, I did this upper problem. So if you want to see 2.2, you could watch the earlier live stream. So now imagine a block is kicked and it slides up the ramp. Just after the kick, so this is after the kick. So the foot is over here now. It's no longer touching the block, okay? So you kick this block just after the kick, it's moving. It's moving up a ramp of length L with some unknown initial velocity, V naught. The acceleration is G sine theta, directed down the ramp, as shown. The block slides 3/4 of the way up, comes to rest before coming to rest. Angle is theta. Determine initial velocity in terms of L, G, and theta. Whoa, that seems different. Notice there are no numbers. Keep your eye on the prize. What are we supposed to get? V initial. Now notice in this particular problem, I'm going to highlight something here. This is what the computer is showing is the X direction. Now, you normally do not do this. Most students do not think of X as going diagonally upwards. I'm telling you right now, this makes this problem a lot easier, right? Instead of having to figure out both X's and Y's as it move, by rotating the coordinate system, as we do all the time in physics, we now have changed a two-dimensional motion problem into a simpler one-dimensional problem. So we're going to do this all the time where we take a coordinate system and rotate it. All right, so that's one thing. We're looking for V initial X, right? That's what this says. You're supposed to recognize that from the words of the problem. Now it says, let me do a little bit more here. Whoops. It says in terms of L, G, and theta. What does that mean? That means L is a known, G is a known, and theta is a known. You're supposed to pretend those are numbers that you know, okay? So again, look at this problem. It says the length L. When it says that, you're supposed to then assume L is a known quantity. Now here, it clearly states that this is unknown. And it looks like I used the symbol V0 in this case. Okay, that's fine. So you could say we're looking for this thing. That's what we're looking for, and it's unknown. How do I know it's unknown? Because it says it's unknown. All right. Now this one, G and theta, those things are given to us, so we're going to assume those are numbers that we would ultimately know. Why do we do problems like this? If I could go to the top of this page, I will show you why we do this. You don't like it? I don't care. You got to get good at this because it's the right way to do things. Why? Once you get good at it, it's faster. 2, it's easier to check your work. 3, this is given in terms of parameters we can change. And so you could use this to make a design. Like you're taking this class probably because you want to be an engineer or maybe a computer scientist or something. You want to be able to change the numbers afterwards so you could test different cases and compare them. Now, at this simple stage, it's almost as easy to always plug in the numbers. I won't lie to you. It's so fast when you plug in the numbers, yes. But in practice, we've got to learn how to do this technique for this reason. And obviously, if you want to make a computer program, we don't want to always have to hard code the numbers in our computer programs. So we need to learn how to write equations for the computer to use, not just numbers. So that's what's a little bit annoying about physics class. Your job is to write the equations that a computer would use. Think of it that way. Yeah. All right. So let's get back down here. I'm going to draw the picture. You do what you want to do. I'll catch up with you. Okay. So don't look at my whiteboard while I'm writing. Question 2.3. Racia. Got a ramp. If you're wondering where I got that G sine theta from, it turns out we're going to learn that in chapter 5, okay? So for now, let's just assume that's a number you're given, and I promise before this class is over, I will teach you how to know that. But for now, let's assume that's known. All right, I'm going to share my screen and see if you do the same picture I did. This is what I'm thinking when I see that. What am I doing? I draw all the picture. I make sure to include the problem number. These are the things that the problem said were given. This is what to find. We're looking for V0, which we said was the same thing as V initial X. Watch out. This problem said the distance, it goes up 3/4 of the ramp. The ramp is length L, but the distance traveled is only 3/4 of the ramp length. Watch out for that one. And wait a minute, was this right? This is not right, is it? Did I flip the arrow, I think? My bad.
Yeah, you did.
And that makes sense. Gravity doesn't pull you up a ramp, right? Whoops, my bad. So let's just fix that up. There we go. So notice, this is something students have a lot of trouble with at the beginning. G is a positive number. It is not the acceleration due to gravity. It is the magnitude of the acceleration due to gravity. That's the official Zoom technique for saying magnitude. You got to remember that one, okay? So this is just some number. This is a positive number. The direction is indicated by the arrowheads. Remember in chapter 3 when I kept saying, oh, in physics, we usually do the number here and the arrowhead tells us plus minus. That's what I'm talking about, all right? So I'm going to make my list of knowns and unknowns. And if you could beat me to it, that is awesome. I love that if you could beat me. All right? So try to beat me and be faster than me, and it's okay if you're much slower. We're only on our second problem, right? This was told to be In face-to-face, this would be a lot more fun, right? But whatever, we don't have that. This was 3/4 L. It wasn't the whole ramp. That's the trick on this one. Every problem's got a trick. Every problem is a trick question in a physics class, right? You probably have already realized this by now, even though you haven't been doing many physics problems. The initial velocity here was V0. And I want to emphasize that we do not know what that is. So the problem said, call it V0, but yeah. V final X, wait a minute, I have no idea. Well, let's go down to here. This is, what is the acceleration in the X for this problem? Somebody, Esteban spoke last, so maybe somebody other than Esteban.
G sine theta.
And that's not right. Somebody else. Do you know why it's not right?
Negative G sine theta.
Yeah, G sine theta is the size of it. That's a positive number. And then we have to do negative because I called this way positive, but the acceleration's going that way. So again, the acceleration is going, this is the positive X direction, but the acceleration's going, oh, I got to get this all on there. This is critical. That's the positive direction, and that's the direction it's going. So you can see that that's a pretty negative experience right there. All right, let's get back to it. So this should be negative G sine theta. G is always positive, always positive, always positive, always positive. The negative came from the arrowheads. Okay, that's where that came from, the negative sign. Do I know the time? I don't think anything told me the time, right? And then do you guys know what V final X is?
0.
Yeah, this is tricky. Like, remember I said usually you know 3 things? We know 2 of them. How did you know this was 0? What was the key words that maybe made you think of it?
It slides 3/4 of the way to the top before coming to a rest.
Yes. So there was something in the problem where it says those words, right? The words are what gave you that clue. And this is classic physics. 2 of the things it basically straight up tells you. The third of them, you have to read between the lines to interpret the word problem to get that third known. And sometimes you have to do that for 2 of the 3 unknowns. So yeah, great job. Great job. Any questions on this setup phase? Nice. Next step, write the equations. I'm going to do that over here. Now, you might not be used to this, but try writing them, but leave like a couple empty lines between them. So like write an equation, skip a couple of lines, write an equation, skip a couple of lines, etc. So my 3 big equations for these problems are always the same. Are there other ones? Yes. But do these solve every problem? Yes. So skip a couple of lines. And I'll scoot this back. All right. Sorry, there's some weird glare there. I don't know what that is, but let's just deal with it. All right. So I've written my equations and I've given myself plenty of space in between. Does anybody remember what the next thing I do is before I start doing math? Maybe somebody, there's been 2 people speaking up today. Maybe somebody other than those 2.
Plug in the zeros.
Yeah, awesome. So let's get rid of that 0. Nice, whoever that was. So V final X is 0. Let's get rid of anything we can. Make life easier. I think that's it. Next. Okay, that was good. Anybody else have any ideas? What might you do next? And there's lots of correct answers here. So, and it doesn't matter if you're correct or not. What do you think you might try? The more you speak up, usually the more you learn. So if you could try to force yourself, that'd be cool. What do you think we might try next? Somebody new. And we can wait you out. It's cool.
Plug in the delta X.
Plug in the delta x. That's a great idea. So let's just, do you agree we have delta x? That's something we could plug in. Outstanding. I don't know who that was, but that was perfect. That was a great idea. I'm going to go even one step further. I'm going to just, before I do that, check the kinds of things I could plug in. So he's starting to think it's time to plug in. I absolutely agree. Before I do that step, sometimes I like to check. I know that the x is there, and I know that I know a, right? Because I know g and sine theta. So I'm going to check this one. I know that. I know that. I know that. I don't know the time. So I'm going to go through and mark the time with a question mark. And I don't know V0. Oh, whoops, here's another one. Which means I don't know V initial, right? Okay, so based on that information, which equation is looking the most promising?
The third one?
The third one, right? So take a look. Here, there's two things I don't know. Too hard for me. Here, two things I don't know. Too hard for me. Down here, I know two things. There's only one thing I don't know. This is the way to go, right? So let's take a look at that one. All right, so because I don't have enough room to do, and what's another thing we should do? Reread the question. What are we trying to find? Fortunately, I already wrote that down up here. We're looking for V initial, right? So let me put a star by this. Keep your eye on the prize. What are we trying to find? We're trying to get V0, which that even makes me happier. So not only is this equation the only one that's doable, it also happens to be the one that solves our desired question. So we're definitely going that way. So at this point, I need to erase. I've run out of room. I would point out, what if you were supposed to get the time? If you had to get the time, couldn't you do this, plug it in there, and then get the time? You bet you could. So if you were looking for time instead, you'd probably still start here and then go to that, but whatever. So I'm just going to rewrite this up here. And now that we've already plugged in that 0, whoever said that was a great idea, because now I don't have to write this crap. And then I'm just going to plug in this problem. We said it was V0. You could keep it as V initial x. And in this case, there's a 2. I'm running out of room. Sorry, I ran out of room already. Geez. A sub x was negative g sine theta. Three-quarters L. And this looks a little bit weird, but so you're supposed to be remembering in your mind, these things were given. This is in theory known. It's a number we could plug in. Theta is going to be some number we're going to know later, and the length would be some number we would know, okay? So I'm going to go ahead and keep going here. We're trying to find V0, right? So I might as well bring this crap to the other side, which will get rid of the minus sign. Or you could bring this one over. Actually, let's do it that way. We should probably clean up that 3/4 and the 2. Maybe we should do that a little bit, but let's clean this up a little bit. At this point, any order, you can do things any way you want, right? So basically, after you get this, just get the job done any way you can. I don't care how you do it. Now, I want to watch out for something right here. Be aware, in a physics class, you see this all the time. I expect you to know that this is the same thing as negative V0 squared. So the squared, you do it first, and then you do the negative. It is not equal to negative V0 squared. So negative V0 squared is negative V0 squared. It's not negative V0 squared. Don't you love physics? It's crazy. But just be aware, when you see this, PEMDAS, right? Exponents come before multiplying by -1. You're good to go. Okay. All right, so there's that. Now, I see some ways we can clean this up. You probably do too. There's a plus sign. Let's do that. And then 2. So now rewriting. Now let's just write this. The color coding is not going to make sense anymore, so who cares? And now I'm going to take the square root. Hey, you're falling asleep out there, right? Watch right now. Anytime you take the square root, always think about plus or minus. Most of the time, plus works. In a physics class, about half the time, it doesn't. So you really need to pay attention to this more than you did in your math classes. Okay, so, or at least as much as you did in your math classes. I want to add, so anytime you take a square root, you have to think. God forbid, you have to think. That's the worst. Let's go back here and look. Initially, this block is moving that way. Should the initial velocity be positive or negative? Anybody? According to this picture,
Positive.
positive. Well, remember, these are not distance, speed, and acceleration magnitude. This is displacement. It's a vector. There's a hidden I-hat. This is velocity, initial in the x. So this is a positive in this case. In this particular case, it's moving in the plus direction in that picture, and that's why we're going to have this thing. So I'm just trying to get rid of a little of that glare, and it's just sucking. Yeah. So in this case, we want to use the plus because in the picture, it's moving upwards. So that's how I know to do that right there. All right. So what are the things we're supposed to check in a problem? Let's go back and look. We did our work. We solved algebraically. Check the following things. The minus sign, didn't we just check that? And what about the units? We didn't check that yet. So let's check here. So I've run out of room, so maybe I'll just do this. Okay, so in this case, I want to check the units. All right, so now we are at the square root of the units of 3/2. That's nothing. This is length. What are the units of length? Meters. And then the units of g are meters per second squared. That's just a number. The units of a function are no units, so they just disappear. Well, that's meters squared per second squared, square rooted. The units check out. All right.
Should we have done that before we started plugging in? That way we don't screw ourselves? Or
You could. To be honest, most of the time you're going to get this right. So in my experience, I usually like to check before I plug in any numbers, just right at that last step. Just because experience dictates, usually you'll, yeah. So, but what you can do is, if this problem got really long, you could bet I would be checking my units like every third, fourth step,
okay.
just like you mentioned, I think, right? So what he's saying is, could I have just checked that right here? You bet. But then you're still going to have to check it down here at the end. And since this one is only 1, 2, 3, 4 lines of work, you know, every 4 lines of work, checking your units, that seems about right to me. You don't want to be checking all the time, but definitely every answer. Is that good on that?
Yeah, perfect. Thanks.
Yeah, absolutely. Definitely check it anytime you want. Other questions? So one of the things that's weird about this, that's the answer. We're not plugging in any numbers. What might you do with this? You could use this and punch this into a simulation and say, look, I want to run a simulation where a block goes about 3/4 of the way up a ramp. All right, let's see, what should it be? Blah, 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 blah. And then you can punch it in and make your simulation run correctly. And you could make the computer do the calculations. You could say, well, the ramp length in my code is this. I'm on this planet, run it this way, and I want this angle for the ramp, blah, blah, blah. And it'll do all the work for you. All right, that's good stuff. Let's see how we're doing. We're doing all right. We got 15, 16 minutes left. On the second line of work, it went from negative. Yes, Adrian, good question. So right here, I think he's talking about right here. Remember, do you agree? So Adrian, I moved this over here, which made this negative. And then I see that I have this negative and that negative, and that's what canceled those two. So again, this negative is canceling with that negative. Let me see if that answered that. Did that make sense, Adrian? Or yeah, right on. Always good question. Good. And so much of physics, as you probably figured out from the quizzes, is worrying about your minus signs, right? It's hard to underestimate how important it is to get your minus signs right. Yeah. All right. Okay. I want to do a couple more things before we get you out of here. Let me go back to a screen share here. This one. All right. You could do all these problems on your own. Imagine this, right? How did I generate this table? I had to do the problem algebraically so that I could generate all those numbers. These problems you could do on your own. There's some tricky stuff in there. It's good stuff. I want to start here at free fall. I don't want to spend a lot of time on this. I just want you guys, we will talk more about it as time goes on, especially in the next class, but I want to get to problem solving techniques, which this class is about getting your math chops ready. So we'll focus more on the physics in another class. But so free fall means gravity is the only force acting on the object. Okay, so now in practice, this is not so easy, it turns out. So for example, let's say I take this eraser and drop it. What do you think? When I let go of this, is gravity the only force acting on the eraser? Your thoughts?
No.
No, what's the other force?
Air resistance, I guess.
Air resistance. Now, if I take an eraser, which is made out of foam, it's very light, or a piece of paper, right? We can see the air makes a huge difference. However, if I drop this coffee cup on my head, it would hurt, right? Because air resistance is pretty negligible for the coffee cup. So in that case, air resistance is not zero, but it's so close to zero, the problem is approximately free fall. And so what are we going to be doing over and over and over in a physics class? We are going to make approximations so that problems are doable in a timely manner, and the answers are not correct. They're approximately correct. They give you a good idea about something, maybe not the perfect exact answer. So nothing that we're doing here is exact, because unless you have a giant vacuum chamber, which I'll send you a video maybe in the email after class of a bowling ball and a feather being dropped in a vacuum, you could actually see that they do fall at the same rate in a vacuum. But most of us do not have a 3 stories tall vacuum chamber like NASA. So for the rest of us, there's approximately, right? So let's look at these questions really quick and see which of these things are free fall. All right. If a plane is flying, hey, is air resistance negligible for a plane that's flying? What do you think? Probably not. Oh, sorry, I stole your thunder there. I'll do a couple of rhetoricals. If you drop a rock from a short building, do you think air resistance is negligible? Go ahead and unmute for this one. What do you think?
Yes.
Yeah, so this one is free fall. How about from a very tall building?
Yes.
Yeah, I would say kind of approximately and say maybe. It depends on just how tall and how dense the rock is. Right? If you drop pumice, maybe that's not as good as dropping granite. All right. How about the beginning of a rocket launch? If the thrusters are on, no. And then somebody else. How about the moon orbiting the Earth?
No.
Yes.
Oh.
How much air resistance is there in space? None.
Nothing.
Now this is what makes people kind of confused about this. No air resistance. The idea is the only force out there is 1 molecule per cubic meter. Imagine you take your refrigerator and put 1 air molecule in there. That's approximately how much how much air molecules are in space. So it's not that there's no air resistance, it's just completely negligible. So the vacuum of space is very close to absolute. And so as the moon is orbiting, gravity is pretty much the only thing pulling on it. It's falling towards the Earth. It just never hits because it's going so fast. Just like the Earth is falling towards the sun, right? Think about the path. If you had a planet here and something orbiting it, right? Here it is moving and it falls towards the planet all the time. And it's just not hitting. So anyways, yeah, all right. So this is actually a free fall. All right, that's great. Let's move on here because we're running out of time. So if you want, you can read more about that later. It's surprisingly interesting. And again, I'll try and send you a video of this soon, okay? Maybe right after class. I know a really cool video. This problem is a good one. You know it's good because it has parts A through M. This is one you should do. All right. So, and let me see what the chat says here. Yeah, right. Totally. All right. So let's take a minute. And I do notice that the first part of this problem is sketching it. So I just want to mix up the lecture from last time. In the first lecture, I did part A and talked about part B and C, I think. So what I'd like to do for this lecture is I want to do part A and then skip to part D. All right, so we're going to do parts A and D. The other lecture video did parts A, B, and C, I think. So, okay, that said, we're doing parts A and D. So notice we're looking for the time of the entire flight. What I'd like you to do right now is read the question. You draw what you think you should draw. I'll draw what I think you should draw, and we'll compare. Try not to look at the solutions when you're doing this, just so we can get a check on how good you are right now. Okay? And then if you've already done it, cool. That's cool, whatever. Still reading. Got it. So hopefully you drew something a little bit like this. This is how I view this problem, okay? I see that this thing starts 2 meters off the ground. It gets thrown upwards, so I drew a little arrow. Maybe you didn't do that, that's fine. And I just called this V0. I didn't see any numbers, so I just labeled it V0. I gave it a name. That way I could refer to it easily. It says it went up to the top at max height. And rather than draw the line straight up and down, what I did was I just kind of stuck in this little bit of space just so it's slightly easier for me to label. It's not going like this. It's going straight up and down, but this is easier for me to visualize. So that's a good cheat that you might do, is just put in a tiny X displacement, even though it doesn't really go that way. Notice I indicate this is just before impact. It's not, obviously when it hits the ground, it's gonna stop, right? So when I drop this thing, it's gonna, well, let me see what, when I drop this eraser on here, it eventually stops. But just before it hits, when it's 1 millimeter above the ground, it's still moving downwards. So that's what I'm trying to draw right here. Just before impact, 1 molecule height above the ground. All right. And now I've drawn my picture. I've labeled it. The next step is list crap. This time we're going up and down. So I'm going to do Y labels. And I'm going to do one more step. Even though most of us are probably thinking this, let's draw it to be explicit since we're learning. Most of us think this is the X direction and up here is the Y direction. So I'm just going to make clear, we're assuming X is to the right and Y is up, just because I'd hate for that to be something that we get lost on. So I'm just being clear about it, over communicating. And then just so I have room here, I'm actually going to put this over here. There we go. So
is this a two-part problem because it goes up and then goes down?
I don't think, so that's a good question. That's one way to do it. So I don't know who that was, but yeah, you could split this into 2 chunks if you wanted. He could say, do one problem from here to here, and then do another problem from there to there. What I think you'll see from me writing this out is you don't have to do that. That's not to say that it isn't a correct method and that it would work, but sometimes this is actually faster. And let's see if we can find out. But you're absolutely right. You could do it that way. Is that good on that?
Yeah.
Right on, right on. Okay, so for the entire flight, somebody new. What is delta Y? Somebody different. What do you think? Take a guess. It's okay to be wrong. What do you think? Delta Y? Anybody? Anybody?
Would it be
4 meters?
Not 4.
I would say 10 meters.
Nope.
Oh, wait.
So notice,
In one step,
right?
12
It's
meters.
tricky.
Oh, because
Nope.
we're talking about displacement, huh?
Yes. Remember what is hidden inside of here. This is not easy. I want to point this out. So everybody out there that doesn't unmute and doesn't talk, remember, these guys are doing it all the time. Now that they screwed up, they're going to be better at it. So don't be shy. It's okay to screw up. I never screw up. I screw up every day. So you're going to screw up too. This has a J hat hidden on it. J hat hidden on it. J hat hidden on it. Remember that? Time obviously doesn't. This means not how far it traveled. It is not the distance. It is vertical displacement vector. How much did the position change?
So it'd be -2.
-2. You went from here and then you displaced +4, but then you also displaced -6. The net displacement is -2. Spicy, eh? You went downwards 2 over the entire flight. Notice this is different than what you might be thinking. So Yeah. This is an unknown. Now I called this positive V0. I don't know what that is. At the end of the flight, I don't know what it is, but I'm going to call this negative V final. Well, I don't know. Let's just leave it as a question mark. I don't want to get confused with those minus signs. How about I just say, I don't know what it is. What is the acceleration in the Y direction? What's causing this ball? Negative G. Excellent. G is the size of it, and the direction is downwards. So again, the planet pulls it down with this magnitude in this direction. Again, this is up, that's down. We see that you get that minus sign from the different directions. So this is not G, it's negative G. The G is the 9.8 meters per second squared. That's all right. And then time. Oh, go ahead.
Wouldn't it be positive G on the way down?
No.
No.
Gravity pulls you down. And in this problem, we said up is up. So now what will change is this. Okay, hold on. Just give me a second. Do you agree we don't know the time?
Yeah.
Okay. So in this case, yeah, we're looking at some, okay, anyways, we'll come back to this in just a second. In this case, we may actually have to do 2 parts like Jacob suggested, because when I'm looking at this, I see 1, 2, 3 things I don't know. We're going to have to do 3 parts. Now going to Esteban's question. In this case, he says, wait, shouldn't G be the other way? No. Watch this. Let me just show you here. And then that'll probably be class today. So now what I did here, this is a simulation. So what I'm going to do is I'm going to launch this thing and play it in slow motion. It's not exactly the same problem, and I think I might need to slow it down a little bit. But so when I watch this one, I'm just going to pause. Now it's not straight up and down, so it's not perfect. But in this case, on the way up, your velocity is greater than, I can't read that at all. The velocity is greater than 0. It's a positive number, right? It's upwards. The acceleration is less than 0. It's a negative number. It's negative G. And it's slowing down. Velocity is positive. Acceleration is the opposite sign, slowing down on the way up. Let's keep going. Now it's coming down. And notice, if we wait a little bit there, and again, forget the little angle there. That's just so I can see it, okay? Notice here, acceleration is less than 0. The velocity is also negative. They're both going downwards, and it's speeding up. That, my friends, is this stupid little chart that I was drawing and I occasionally allude to on page something or other. Right there. When they're both negative, you're speeding up. Esteban, does that address your question?
Yeah, definitely. I guess it's just like it's intuitive to think that since you're going towards gravity, that should be positive, but it's because velocity is negative and acceleration is negative, which is why you're speeding up towards the ground.
So the shortcut, I think, when I'm trying to think about whether something's speeding up or slowing down, I don't think about the signs by themselves. I think about them relative to each other. If they have the same sign, speeding up, opposite signs, slowing down. Let's go back to this and watch that simulation one more time. I know it's time to go, but let's just, whoops. Let me do this, erase this. Let's have a little bit of fun here. Let's shoot a car, okay? And so now I'm gonna run this one again, and I think we're ignoring air resistance right now. You see that that has air resistance. We're gonna ignore air resistance. So when I shoot this thing up here, slowing down, slowing down, slowing down. What is the velocity at the top?
Should be 0, no?
Yes. somebody else, what is the acceleration at the top? That's trickier, isn't it? He got the easy one. Yeah. At the top, let's watch. Oh, whoops. Oh, whoops. Oh, crap. Oh, this is going to be kind of cool. We got Buicks going everywhere. Notice the acceleration at the top. It's not zero. The velocity goes to zero at the top for a split second. Let me just step this through here. Now, obviously, there's a small displacement in the X here, so that's screwing this up. Let me reset this. And I'm going to shoot this straight up and down. So if you go straight up and down and I fire this thing, and let's do something easier to see. How about a pumpkin? Okay. Oh, let's do human. Okay. Oops. Oh, gosh, sorry. Let me do this. I'm trying to hit the pause button. I keep hitting the fire button. As this person goes upwards, look at that green arrow. That's the velocity, the green arrow. Sorry if you're green colorblind here. I could talk about it again in a different way. Right at the very top, velocity goes from positive to zero to negative. And so for a split second, the velocity is zero in the vertical direction at the top. And then as this thing keeps going, we see it speed up. All right, so let's leave that at that. And we should probably, well, I'll leave it open. Anybody that wants to ask questions, but feel free to take, go ahead and take off if you need to take off. If you have questions, Memo. Remember, you can contact Memo anytime, get that free tutoring. Man, the sooner you do that, the more, just take some of your frustration away. So Memo, throw your email in the chat again, will you? And just tell them, hey, you contact me, and you could talk to them outside of class. Yeah, any other questions from anybody else?